Okay, scholars, what I thought we would do real quick is just try to clarify um, one important thing about rotation, a specific type of problem with rotation, um, a problem involving pulleys. We've kind of already seen this. We did a couple of these problems in the previous video, but I wanted to take a moment just to really clarify and make sure that everyone is on the same page. Remember that we had this specific setup known as an Atwood's machine that we analyzed earlier when we just had a unit on forces. Here's a pulley, here's a rope strung over the pulley, and the Atwood machine has, two different masses here, M1 and M2. And let's say that mass 2 is greater than mass 1. We know, therefore, that the whole system will accelerate this way. And remember how we analyzed this. We drew a free body diagram for mass 1. There was a force of tension going up, a force of gravity on object 1 equal to m1 little g. And we said that we wanted upward to be the positive direction because this mass 1 is accelerating upward. Draw a free body diagram for mass 2. Force of gravity on mass 2 equals to m2 little g. And then we had this force of tension. And over here for mass 2, we consider downward to be the positive direction. Because mass 2 is more massive, it's going to be accelerating downward. And here's the important thing. We were completely ignoring the pulley, ignoring any effects from the pulley. And we therefore just said that these two tension forces from the ropes were equal. In other words, the rope has an equivalent tension force all the way throughout. That is only true if we ignore what the pulley is doing. If the pulley is, as we say, frictionless and massless, in other words, we don't care about it, then and only then is this analysis true. Another way that we analyze this, let me remind you, is that we collapse this thing down into one system that we called mass 1 and mass 2. And we viewed it like this. We just wanted to view the external forces, the forces external to the system. That allowed us to ignore the internal tension force that is just between the two particles. And we said, okay, well, there is an accelerated force downward trying to get the system to accelerate. That's the force of gravity on mass 2. And the resistive force resisting that acceleration would be the force of gravity pulling back the other way on mass 1. And they are both only valid if the pulley does not make a difference. If the pulley is massless, frictionless, if the pulley is ignored. Let's see now, though, that this whole setup must be analyzed in a different way when the pulley is no longer ignored. So let's look at an Atwood's machine where the pulley now has mass. Okay, so when we start to analyze the Atwood's machine with a massive pulley, this time we're going to have to make 3 free body diagrams because basically by saying that our pulley now has mass, it is an object in our system. We're going to have to treat each object independently and analyze them using Newton's laws separately. So we can very easily do this for mass 1. And once again, let's say that mass 2 is greater than mass 1 in this case. So mass 1, I have force of gravity acting on mass 1, which will be m1 little g. I have force of tension. Let me do mass 2. Okay, so remember when we ignored the pulley, we said these tension forces are the same. But this time, that is not the case. This is hugely important. You guys must get this down. If we are not neglecting the pulley, if the pulley now has mass, what is it going to do? Well, it's going to rotate. It's going to spin. Let's say that it's anchored right here. That's like an axis going through it, an axle going through it about which it can rotate. So the pulley itself is going to be able to spin around. It's going to be able to rotate. And I hope you guys can understand that if mass 2 is larger than mass 1, then the rope is going to be going around this way. In other words, I'm going to have acceleration down here, acceleration up here, just like we had last time. I can add that to my diagrams over here. And those accelerations will be the same. That's still true. But that is going to cause, the rope is going to cause this pulley to rotate. So the pulley is going to have a change of rotational motion. The pulley is going to have an alpha, a rotational acceleration now. And it's always going to be spinning around in the direction of the acceleration of your object. So mass 2 accelerates downward, mass 1 accelerates upward. The pulley, of course, is going to be spinning here clockwise in this example. Well, what's the only thing, you all, that can cause an alpha, that can cause rotational acceleration? Torque, right? Well, where is the torque coming from? Remember, torque is a force applied at some distance away from an axis of rotation. Here's my axis of rotation. It's always got to be the first thing we think about with rotating objects is where is the AOR, the axis of rotation. Torque is some force applied at a distance away from that axis. So what forces are being applied to this pulley right now? Of course, the pulley is like it's held up by some support mechanism. Gravity's pulling it down. I'm not worried about those forces translationally. I know that the pulley is not like falling or being lifted or anything like that. So I'm not worried about those forces. Those forces are acting on the center of mass anyway. So what forces are acting away from the center of mass, away from the axis of rotation, that can provide a torque? Well, it's the rope. If I draw a free body diagram for the pulley, where the pulley has radius r, and once again there's the axis of rotation, then I see that there are two torques. This rope is strung along here, and then right at this edge, the rope is interacting frictionally with that pulley, with that part of the pulley right there. And so I can label that FT2. It's the same tension force that mass 2 experiences here. Think of Newton's third law. If the mass pulls down on the rope pulls up on the mass with the same tension. So these two forces are the same. And then where else is there a possible torque that's acting on the pulley? Yeah, right over here, the other rope, FT1. This rope applies a frictional interaction to the pulley, trying to get the pulley to rotate back the other way, doesn't it? So you can see then that these two forces must be unbalanced, because what is the pulley actually doing? The pulley is actually rotating. What causes rotation? What's the only way you can get rotation? You have to have a net overall torque, don't you? When your alpha is non-zero, there must be a net torque being applied. Where's my net torque coming from? It's coming from this tension force over here on the right, FT2. So I can no longer treat FT1 and FT2, the tension forces in the rope, as the same. They are actually different. They are different. And that is where this gets more complicated. Last time we neglected the pulley, we were able to say those tension forces were the same. Now, because we are thinking about what the pulley's doing and thinking about the fact that the pulley is rotating, the pulley has an alpha, rotational acceleration, it's changing its rotational motion. It must therefore have a net torque. What's the only thing that could cause the net torque? I must have unbalanced torques supplied by the interactions with the ropes, the tensional, frictional interactions with the ropes on the edges of the pulley. Okay, so I know that therefore that these forces cannot be the same. They have got to be unbalanced to yield an unbalanced torque so that there will be an alpha. So what I need to do now is write equations for these things. I hope that you guys are able to draw a free body diagram like this for the pulley. We haven't done this a whole lot, but this is something that you're going to have to get used to doing when we're analyzing rotation. Rotation is all about torques, and a torque is all about a force applied at some distance from the axis of rotation. You're going to have to represent your object as an extended body. The shape matters. The arrangement of its mass matters. So it's fine to treat mass 1 and mass 2, these blocks, as just point particles, collapse them down into little point particles, because we don't care about their rotation. There's nothing that could cause them to rotate. But here, this thing is rotating. It's changing its rotational motion. It has a rotational acceleration alpha. And so we have to draw it like an extended particle, like an extended body with shape. The shape matters. And we are worried about where on that object the forces are located. All right? So let's start writing some equations. For this object right here, that equation is going to be pretty simple. Let me scroll down a little bit. For that object, the equation will be pretty simple. Remember, it's accelerating up. So I want up to be positive. Newton's second law says that the sum of the forces equals mass times acceleration. So I'm going to get Ft1 minus m1g. That would get me the sum of the forces equals m1a. So there's one equation. I can repeat that process for the second object's mass 2. Newton's second law equation, the sum of the forces equals mass times acceleration. This time down is positive. The direction of acceleration is positive. So m2g minus ft2. Once again, the tension forces are different this time. Equals mass times acceleration, just like that. And now I'm going to write an equation for this guy right here. This is the new thing for you all. So when I write this, I'm going to write a torque equation because it's Newton's second law for rotation. So I always want to treat, just like always, I want to treat the direction of acceleration as positive. So which one of these is going to be responsible for giving me a positive torque? This one right here, right? Because that one is causing the rotational acceleration. Does that make sense? I know the thing is rotating clockwise. This is the only force that could be supplying a torque to cause that rotational acceleration. This one is resisting that, so this one needs to be my negative resistive torque. Remember that torque is defined as R cross F, where that simplifies to RF sine theta, where theta is the angle between those two vectors. And remember what the R vector is? It's the vector from the axis of rotation to the point of application of the force. Well, here it's pretty clear that the force, here's the axis of rotation, here's the force. If I draw a line from the axis of rotation to the point of application of the force, it's going to be perpendicular to the force already. That's a right angle. So my theta there would be 90 degrees, and of course the sine of that is just 1. So my torque, therefore, is going to be RF, R times whatever the force is. So here's my Newton's second law for this. I'm going to sum up the torques, just like always. My positive torque is going to be the torque supplied by this tension force 2. So it's going to be R Ft2. And then I have a resistive torque over here that's resisting that angular acceleration. And that's going to be Rft1. That is my net torque. That is my sum of the torques. Please pause and make sure that this makes sense to you. This is the torque caused by this tension force 2. This is the torque caused by tension force 1. They oppose each other. I'm considering this one to be positive because it's responsible for the angular acceleration. That equals I alpha. I is the rotational inertia. My pulley is a disk. So the rotational inertia for a disk is 1/2 m r squared. We have three m's now. Let's pause and make sense we know what they are. Make sure we know what they are. M1 is the mass of this box. M2 is the mass of this box. M would be the mass of the pulley, all right? M. R is the radius of the pulley. So that's I, and then here's alpha. Just like that. All right. Now, the problem right now is I have three equations, 1, 2, 3, and I have four unknowns. I have my tension force, my other tension force, acceleration, and angular acceleration. That is four unknowns. I don't have enough equations. So I'm ultimately trying to set up a system of equations that will allow me to solve for these things. But it turns out that I can put this alpha in terms of something else, can't I? I want you to think about this. These two boxes are still going to have the same acceleration because as long as there's no slack in the rope, as long as my rope is taut, every piece of that rope has got to be accelerating the same. It's not broken, it's not slack, so every little bit of that rope must be accelerating the exact same. So my A value is the same here. Even though the tension forces are not the same, the A value is the same still. Well, then it also has to be the case that at a point on the edge of the pulley right here, it must also be accelerating down with that same acceleration, correct? And don't I have an expression that helps me find the acceleration on an edge piece tangent to the object? Don't I have an expression that relates that with rotational acceleration alpha? I do have an expression for that, don't I? This is key. This is what you guys really must be able to do on your own and keep straight in your heads. I know that a tangential quantity is related to the angular quantity by multiplying the radius times the angular quantity. Remember, we've said this lots of times, like the tangential velocity is r omega, right? Same exact thing. How do you translate between a tangential linear kinematic expression and the angular kinematic expression? It's through an equation just like this. Well, A tan here is the acceleration that shows up in these other equations, as I've just discussed and tried to prove to you, that every piece of the rope must be accelerating the same because the rope is taut, it's one object, and a piece right here on the edge of the pulley, therefore, must be accelerating with that same acceleration. So if the pulley has a rotational acceleration alpha, then I can relate those two variables just like this. Okay? So ultimately then I'm able to make this statement that my acceleration A that shows up in all these other equations has got to be r times alpha. Therefore I can rearrange that and say that alpha equals A over r. And I can plug that in right here. And I can get rid of alpha. And now I will have three equations with three variables. So this equation becomes r ft2 minus r ft1. There's my net torque equals the I of a disk is 1/2 mr squared. And then alpha we just said is A over r. So now I have three equations that will allow me to solve for my three variables, where those three variables are ft1, ft2, and of course A, which shows up right here. All right, and we can rearrange this. Obviously, I can simplify this equation here a great deal. We can rearrange these algebraically however we need to solve for whatever we're asked to solve. But what you guys need to do is be able to derive these equations and then manipulate them appropriately. So if I were you, I would practice just the general Atwood machine setup, ignoring the pulley, make sure you have that mastered, and then make sure that you can master this, where the pulley does have mass, and we are no longer able to neglect that mass. The pulley is going to start rotating. Therefore, the tension forces are no longer going to be the same because one of them has got to be bigger to provide that net torque to cause the to cause there to be an alpha, to cause there to be rotational motion in the pulley. And then it's key that you understand how to translate between those tangential accelerations. It's key that you understand why this is true, that the acceleration in the rope, in the masses in the ropes, and tangent everywhere are all the same. And it's key that you understand how to get from the acceleration of this point on the edge of the disc to relate that to the alpha. All right. I'm going to leave it up to you to do the algebra of this. You could rearrange to solve for the acceleration, rearrange to solve for the tension forces, whatever. Once you have the acceleration, you can plug back into here to find alpha, right? Okay, let's look at another very important type of question that you guys are going to encounter quite a bit in your rotation studies. And this is a type of question that involves an object rolling along a surface. Now, we've kind of already looked at a question a little bit like this when we were looking at that spool of thread that was attached to the ceiling, and it was like unrolling itself. We said that one way of looking at it was as if as this thing spins this way and falls down, we said that we can view it as if it's like rolling along the thread, and the thread is not slipping as it rolls off of the spool. So we have kind of already talked about this a little bit, but I thought that we would do it now in a more rigorous and specific way. So basically, when you have an object like a wheel or something rolling along a surface, let's just make it a flat surface for now. There are two possibilities for how this thing can be rolling. The first possibility is that it can be rolling without slipping. You are responsible for knowing everything that is true for an object rolling along a surface without slipping. These things will not be on your AP equation sheet. You will not be reminded of them. You have got to memorize this. The most important things for you to know about something that's rolling without slipping is that whatever its center of mass is doing, the rest of it is also doing. Here's what I mean by that. If this thing is rolling, then we are able to draw little velocity vectors for all these points along the edge of it. So these would be the velocity vectors at a given instant in time. And we can call them tangential velocities because they are tangent to the rolling curved path that the wheel is taking. So if this thing is rolling across the surface without slipping on the surface, then the tangential velocity at any point on the edge is going to be equal to the velocity of the center of mass of the object. In other words, let's say that the center of mass is here in the middle of the wheel. Because this thing is rolling along the floor, rolling along this surface, it has two types of motion. It is rotating, but then as it is rotating, the center of mass is also moving from left to right. So I could draw another velocity vector here, like that, and that would indicate that not only is this thing rotating, but as it rotates, the whole object is moving from left to right, displacing some actual linear translational distance. Does that make sense? So rolling without slippage, as long as this wheel is not slipping over this surface. So an example of something that is slipping would be like you're at a red light, the light turns green, you accelerate too quickly and your wheels just spin on the pavement and the car does not move. Your wheels are just spinning in place. That would be slipping. The surface of contact here of the wheel would be slipping over the floor, over the asphalt in that example. So what I'm talking about is when there's like perfect motion, as the wheel rotates, it pushes off the floor pushes it forward, so the wheel itself has translational motion, it moves. Rolling without slipping, this will always be the case. That the velocity of a point there on the edge of the wheel is going to be the same as the velocity of the center of mass of the wheel. All right? And remember that we have an expression that relates tangential velocity here to rotational quantities. We could say also that this is true, correct? Whoops, that is a wacky omega. Oh, it's freaking me out. R omega, right? And so if this statement is true, and everyone should know this statement, that the velocity on a point on the edge is that tangential velocity is equal to the angular velocity times the radius of the object. This wheel has a radius, big R, okay? Then that must also be the velocity of the center of mass. So this is true, and this is true, and this is true. You guys need to know that. These things are only true when there's rolling without slippage, okay? And not only is this true for velocity, but if this thing is also accelerating, if it's speeding up as it rolls without slipping, then the exact same thing is true for accelerations, that a tangential acceleration is going to be equal to the acceleration of the whole body itself. That's what I mean. I hope you guys understand this when I talk about the center of mass quantity, velocity or acceleration, the speed of the whole thing itself, or the acceleration translationally of the whole thing itself. All right. And again, we know that any tangential quantity is equal to the angular quantity by multiplying it by the radius. And then, of course, we can say that this also has got to be true. So all of this is true for rolling without slipping, okay? The center of mass is moving at the same speed or the same acceleration as a point tangent, all right? Okay? Now, this is interesting because what if you were asked maybe to find the actual velocity of this point right here? The actual velocity of that blue point from an external point of view. Well, you have to recognize that from an external third-person perspective, this point is doing two things at this instant, isn't it? Not only is it moving translationally across the floor with the center of mass, but it is also moving with this tangential velocity here. So the actual velocity, and if these two are equal to each other and we let them be v, then the actual velocity of this point here would be 2v, wouldn't it? That would be the instantaneous third-person point of view velocity of that object, of that point on the wheel, 2v. Make sure that what I just said makes sense to you. We just do vector addition, right? The actual velocity here is going to be the result of the two individual constituent velocities it has from an outside perspective. The center of mass is moving translationally, which means that every point is moving translationally, and then it also has this rotational speed that is equal. So the actual speed would be v there. Now here's another interesting point that we have got to talk about. This one is more important. What would the actual velocity overall be for a point down here at the bottom? Well, just do vector addition. The whole center of mass is moving to the right, but rotationally speaking, this thing is moving instantaneously to the left. So if these are the same, have the same size, And really, I'm so sorry. I'm recognizing now that these should have absolute values around them. It's just the size, it's just the speed that's equal. Because here you can see clearly that the center of mass, the whole body itself is moving to the right, but rotationally, this point down here is moving to the left because this thing is rotating clockwise. So what would the instantaneous velocity be right here? The instantaneous velocity would be 0. This is something else that you guys have got to remember that is only true for rolling without slipping, is that the instantaneous velocity of this point on the bottom where the wheel meets the surface, the instantaneous velocity of that point is 0. The overall instantaneous velocity of that point right there is 0. For up here it was 2v, right? If we let v-tan and vcm just be v, they're equal to each other, then you do vector addition and that point there will be moving with a speed from an external point of view of 2v. This one is moving, I have a positive v, I have a negative v, those would add up to be 0. It's not moving, it's instantaneously motionless. Okay, that is only true if something is rolling without slipping. It is instantaneously at rest here. A point at the bottom is a point where the surface meets the wheel. All right, you've got to memorize that. So what I want to do now is analyze this thing in terms of the forces that are acting on it. So again, this is rolling without slipping. Okay, so when my wheel is rolling without slipping, everything we just said is true, and I want you to think about this. Let's say that it does have, as it spins, it does have an alpha. It does have a rotational acceleration. Well, you guys know that in order for there to be a rotational acceleration, there has got to be a torque applied, right? So as this thing is rolling without slipping and it's translating at the same time, it's going to be accelerating linearly as well. What is causing the rotational acceleration here? There has to be a torque. Here's the axis of rotation, right? That is the axis around which it is spinning. So what is causing that torque? Well, as this thing pushes against the ground down here, the ground also pushes back against it. So I have these frictional interactions, these pushing frictional interactions between the wheel and the ground. So if I want to try to draw the force that's responsible for the torque, I'm going to draw it right here. And I hope it's pretty clear to you that it's pointing in what direction. If I want to draw the force on the wheel that's responsible for this accelerated rotational motion, in which direction does that torque have to be pointing? Well, the force have to be pointing that's causing the torque. Well, we know that the angular acceleration is clockwise, so down here the force has got to agree with that. The force has got to be clockwise as well. So down here I'm going to have a force just like this, and again I'm drawing the forces on the wheel. And what kind of force is that? It's a frictional force. Remember, we have two different types of friction, static and kinetic. What type of frictional force do you think this is? Well, remember what we said earlier about this point right here. At every instant, it is instantaneously motionless, isn't it? So that means that I have static friction. Again, that is only going to be true when I have rolling without slipping. There is a static frictional force down here that is causing the torque of the roll. All right? So if I wanted to talk about the torque it would be r cross f, where r, once again, is that vector drawn from the axis of rotation to the point of contact. Those are at right angles to each other. So a cross product, I'm worried about the sine of the angle between them. The sine of 90 degrees is 1. Let's say this thing has a radius of big R. So my torque then is just going to be big R times the force of static friction. And this, I haven't drawn it, but this wheel still has the force of gravity and a normal force acting on it. All right. So the force of gravity always works from the center of mass, and the normal force works from the point of contact. So I'm going to have gravity going down, normal force going up. Those are going to be equal in this case. So my torque then is going to be R. I'm just trying to remind you that a force of friction is always the coefficient of friction, static in this case, times the normal force. And in this case, because my wheel is not accelerating up or down, I know that the normal force is equal to the force of gravity. So my torque then becomes R, coefficient of static friction, mass of the wheel, times little g. Just like that, okay? All right. And I know that net torque equals I alpha. Let's say that this is just a thin wheel. It's a disc. The I of a disc is going to be equal to 1/2 big M R squared. My net torque, that's the only torque I have acting. So R mu S mg equals 1/2 mr alpha, mr squared alpha. Okay, so this is my Newton's second law equation for the net torque acting on the object. R times static force of friction here equals I alpha. And we know that this thing is also accelerating translationally in addition to its rotational or angular acceleration. And of course, in rolling without slipping, we know that this is always true. The acceleration of the body of the center of mass of every piece of the thing translationally is equal to r, the radius, times the angular acceleration. Of course, you guys know that we can rearrange this to say that angular acceleration equals a over r, and I could plug that in right here. And so ultimately I get this equation. And I'm just showing you an example of what we can do now to start manipulating this thing algebraically. And from here, we could solve for multiple things. We could simplify this and solve for what the acceleration is. We could simplify this and solve for what the coefficient of static friction must be, things like that. Let me remind you about static friction. Static friction was weird because remember that your static friction force can change based on the circumstances, the context of the scenario. So you may remember that when we first started analyzing static friction, we had just a simple example like this: a box on the floor. The floor has some friction, and you start to pull the box with a pulling force to the right. It doesn't move, it doesn't move, it doesn't move. You pull stronger and stronger and stronger, and eventually it does move. So what's happening when it does not move? Well, if you are steadily increasing your pulling force as time goes on, we know that maybe at a certain time you're pulling with a certain strength, and the friction force, the static friction force, exactly counteracts that because the box is not moving, so the acceleration is 0. Then maybe you pull even stronger and the box is still not moving. Well, how can that be possible? Well, we know that the net force must still be 0, so the frictional force must have grown in response. So remember that static friction is weird. It changes based on the context. So we had this graph where here's a frictional force, if I were to graph it, and maybe time. And as time goes on, I'm pulling with a stronger and stronger and stronger force. So the frictional force grows and grows and grows and grows and grows up to some maximum value, and then all of a sudden I overcome the static frictional force, and then what happens? I get the thing to move, and then the lower kinetic friction takes over. So remember that static friction can be different, and it reaches some maximum value. And then once we get the thing to budge and to actually move, then the lower kinetic friction coefficient takes over. So please remember that. So this is an interesting thing to think about. This static friction coefficient here is going to be like the maximum. So for every surface that an object is rolling on, there has to be a specific relationship between the static frictional coefficient and the acceleration. Those things have got to reach certain parameters. If the acceleration is too big, then we overcome the static friction coefficient, and now all of a sudden we have kinetic friction, which means that this thing would be slipping. Once again, you guys may be familiar with this. If you're at a stoplight and the light turns green, you accelerate, step on the gas pedal, causing your car to accelerate too quickly, causing the wheel to have too large of an angular acceleration. You know that your wheel will spin out over the asphalt, and it's going to slip. And we're not going to have static friction here. We're going to have this piece actually slipping over the asphalt, and we get kinetic friction. So just keep in mind that this static friction in this equation with the acceleration is kind of talking about a relationship of what the maximum static friction force could be. And if your acceleration overcomes that, then you're no longer going to have this thing without slipping. It is going to be slipping, and all this falls apart. Because important for you guys to know, this statement here is only true when our thing is not slipping. If it is slipping, these things are not true, and the analysis kind of falls apart. All right, so hopefully you are following the explanation of torque. Hopefully you're understanding why there's static friction here, because instantaneously this point here is motionless. We have a translational velocity to the right, but an instantaneous tangential velocity due to rotation to the left. Those are equal, they cancel out. So right here, this point is instantaneously at rest, so we get static friction here. It's pointing to the left because it's the only force that can be causing a torque to cause this alpha, to cause this rotational acceleration. And we use Newton's second law. We use this relationship, which is true because it's not slipping, and we can derive this equation, and we could solve it now for any variable that we wanted to. Okay guys, this is something really important that I failed to mention in this example, but we do need to talk about it. So this will become clear why this is important in later examples, but real quick, let me redraw this. So we said that this thing was rotating around this way, so it had a clockwise alpha, and we also said it was accelerating to the right. And we said that right here, there must be a static frictional force pointing back. That looks like it's pointing down. Let me fix that. Pointing back along this way. And we said that there has to be a static friction force pointing back to the left because it is the only force that could be supplying the torque necessary to cause this alpha, to cause this rotation. It's the only force that is acting here at a distance from the axis of rotation perpendicular to this r vector, or with a tangent component to the r vector. So it's the only thing that can be supplying my torque. And I know that this thing is rotating, has a rotational acceleration clockwise, so this force down here must be causing that clockwise rotation. What we didn't really talk about is, and what I left unsaid, which I should not have, is what's causing the translational acceleration. Well, there's got to be a force to cause that translational acceleration. This force can come from multiple different places depending on the context, but to make this simple, let's just assume now that this is like a bicycle tire. So if you go outside and you look at your bike, you will see that that it has a chain, and that chain is located pretty much close to the center of mass. Um, so we can just say then that there is a force right here, like a pulling force or something, a force of pull located at the center of mass. That is what is causing that translational acceleration. Okay, so everything that we've just talked about is true only when the translational acceleration is caused by a force that is acting perfectly at the center of mass of the object. In future examples, we're going to see what happens when the pulling force is located at the top. Like we're about to see an example where we have a cylinder with a string and we pull the string from the top. Later, we're going to see what happens when we have a yo-yo and we pull the string from the bottom of the yo-yo, and we're going to get some different cases. Friction is actually going to end up pointing in different directions. So I wanted to mention here that I failed to mention the fact that we do have this pulling force that's located at the center of mass here to cause this translational acceleration. And then we said it's rolling without slipping, so hey, what's causing it to roll instead of just skidding without rolling? Well, there's got to be a torque. The only thing that can be supplying that torque then is this force of friction. In these later examples, we will see that that the torque is supplied by other forces, and friction may end up pointing in different directions. So to really find out which way your friction is pointing, you have to look at the big picture context and try to figure out what's causing translational motion and what torque is there that could be causing the rotational acceleration, and think about how your friction fits into that context. Okay, so I just wanted to hop in here and mention that I erroneously failed to mention the fact that this translational acceleration is being caused by some force, maybe a bike chain or something, acting at the center of mass here. Okay? We should pause and look at a few more complex examples of objects rolling across flat surfaces. So let's say that we have this cylinder, and we're looking at the circular edge of the cylinder here, and we've wrapped a string around it. And the string has been wrapped around several times, and there's a free edge coming out right here that we can pull on. So we're applying a force of tension to the cylinder right here, going to the right like that. I want to know what's going to happen to the cylinder. I want to know what is its translational motion like and what is its rotational motion like. Okay, so the first thing that we should note is that I'm pulling it hard enough to actually get it to accelerate to the right. That information, I'm just telling you, I'm pulling it hard enough to accelerate it to the right. So it is accelerating this way. It is moving. I've caused it to move from rest to the right. So I know this tension force here going this way is quite strong. So I want to know just exactly how it's going to accelerate. What is that translational acceleration like? And then what is the rotational acceleration like as well? Okay? So let's think about what this tension force is doing. I know that tension force is responsible for several things. First of all, it's responsible either fully or partially for the fact that this thing is accelerating to the right. And it's also going to be responsible for producing a torque that gets the thing to rotate. Here's how I know that. Here's the axis of rotation, right? And this force is applied right here at this point, which is a distance r, where r is the radius, away from the axis of rotation. So what I have here is a torque, don't I? I have a force that's being applied at some distance away from the axis of rotation. Looks like if I turned this into a vector, it would be perpendicular to my tension force vector. So I could say that the torque due to the tension force is just force of tension times r. Sine of theta collapses here down into 1 since the angle between them is 90, as I've said. And it looks to me like that is, to put it quite simply, that's a positive torque. So I know that because my force of tension is quite big here, I know that this thing must be caused to rotate around clockwise. the angular acceleration is pointing this way, because that is what this torque is doing, okay? Now, what we're interested in is the other force acting on this object. What is the other force acting on this object? Well, down here there's an interaction too, isn't there? There's a force of friction. And please remember that without slipping, it's a force of static friction, because at every instant, this piece down here is truly at rest. It's truly motionless. We proved that earlier. So, believe it or not, this static frictional force, it ends up being pointed to the right. My force of static friction does. Now, that freaks people out, because we've always learned that force of friction opposes motion. And you look at this thing and you see that it's translating, it's moving linearly to the right. So shouldn't this frictional force go back, opposing that to the left? Well, it's more complicated than that, unfortunately. We have to think about what's happening with the rotation. Okay, so this is something you guys have got to get used to doing now that we're analyzing these objects as extended objects and we're analyzing how they rotate. I know that this thing is rotating clockwise, and so right here, truly, in which direction is there a tendency for this point to move relative to the surface? There's a tendency for this point down here to, because it's rotating like this, there's a tendency for this point right here to be moving to the left over the surface. Does that make sense? So because this thing is moving, this point here is moving instantaneously, it has a tendency to move instantaneously to the left and rotate around this way, because once again, my alpha, my rotational acceleration, is clockwise. I know that because this tension force is supplying a pretty good torque to set it in rotational motion clockwise. So if this point here has a tendency to move left, then the frictional force has to oppose that. So the frictional force must be pointing to the right. Does that make sense? So if I was to draw a free body diagram to figure out the translational motion, I can collapse it into a point particle. Of course, I'll have the normal force and the force of gravity. I know those cancel out. I'm not worried about them. And then I'm going to have this tension force pointing to the right. And I get a frictional force, a static frictional force pointing to the right as well. It's actually going to help accelerate my, my object. So the acceleration is bigger than it would have been if this thing was not rolling. If it was just like a box or something I was pulling with the string, then the frictional force would definitely be pointing to the left. It would have no other option. But because as this thing rolls without slipping over this surface, and I have a big tension force here pulling it to the right that is causing this torque, that causes this clockwise rotational acceleration, causing a piece down here to have a tendency to come left, the frictional force has got to be going to the right, helping that tension force. So the linear acceleration then, if I do Newton's second law, force of tension is being helped by that static force of friction, and that's going to equal ma, just like that. Usually we think about frictional forces hindering us, but here it's helping us because of the rotation. Interesting, isn't it? So let's think about how we could express that rotation now. We could write a Newton's second law expression using an extended free body diagram, which I've kind of already drawn. Here's my force of tension. Here's my force of static friction. And those two forces are helping each other translationally. They're pointing in the same direction. But in terms of torque, they're pointing in different directions, aren't they? In other words, here's the axis of rotation. Here is a line drawn from the axis, oh boy, from the axis of rotation to the point of application of my force. If you were to do a right-hand rule for this, for the cross product of these two vectors, then you're going to get a torque pointing into the page. So my torque from the tensional force is pointing into the page. And if I do one here, and I do the right-hand rule, the torque from the static friction would be pointing out of the page. Those two torques are opposite each other. They're trying to cause opposite things to happen. That's clear. You don't have to use the right-hand rule. You can understand this pretty well without the right-hand rule. This force is trying to cause the thing to rotate clockwise. This force is causing a torque that wants the thing to rotate counterclockwise, right? We've already thought through the fact that this force must be winning. This force must be big enough to cause the thing to move in the first place. So it must be winning, causing the thing to rotate around clockwise. We've already thought through that idea. So my Newton's second law equation for my extended free body diagram, where I've actually drawn the thing and I'm thinking about, you know, the distance away from the axis of rotation that these forces are, I'm going to say that the net torque equals I alpha FTR would be the torque from my tension force minus F, my force of static friction, R, is got to equal, let's say that it's a cylinder. This is something we haven't talked about. This is really important. Here's a really crappy sketch of a cylinder. Let's say it has length L, and it's rotating, you know, about this axis, going like through its middle, right? Does the length of the cylinder have any bearing on the I value, on the rotational inertia value? No, it does not. It doesn't matter how long the cylinder is, as long as my thing is rotating about, you know, the middle of its circular edge. Remember what I is all about. It's about how the mass is distributed about the axis of rotation with respect to the axis of rotation. Doesn't matter how I extrude the cylinder across along that axis. Doesn't matter how long the cylinder is. The mass will still be distributed in the exact same way. So, in other words, what I'm telling you is that if you have a disc that is just like this, like a coin, and it's spinning about that axis, or if you have a really long cylinder spinning about that same axis, the length does not matter because you get the same mass distribution away from that axis of rotation, and that's what I is all about. So we don't care about the length of the cylinder at all. It's just going to be the I value for a disk, which is 1/2 m r squared alpha, just like that. So these would be my Newton's law equations for this scenario, and then we could analyze it quantitatively. I wanted to analyze it more qualitatively, more conceptually, to make sure that you understand how we can predict this confusing bit here where the force of friction actually points to the right. All I thought through was this. I said, hey, this force of tension is big enough to cause the thing to translationally accelerate to the right. It must be a big enough torque then to cause the thing to rotate with it. It's going to cause rotation in a clockwise direction. So what's going to happen down here at this point of contact, where the cylinder contacts the surface? Well, I know that this point here has a tendency to, because of the rotation, which I figured out from this torque, from this tension force, because the rotation is clockwise, I know that there's a tendency for this to move left and up. And so the frictional force has got to oppose that, right? So we're using the same rules that we've used before. Frictional forces oppose relative potential sliding motion. It's just that we need to undergo a more thorough analysis with objects that are rotating. As this thing rotates in a clockwise direction, this piece down here wants to move left, so the frictional force has got to be pointing to the right. And here we can see that that actually supplies an oppositional torque, a torque that is opposite what the tension force is doing. They help each other translationally, but they oppose each other rotationally. And that has led us to these Newton's second law equations. Newton's second law for translational linear motion, where the two forces add together to a net force. And here's Newton's second law rotationally, where the two torques counteract each other. All right. So hopefully that was an example to help you kind of see what you have to pause and be careful that you think through what the rotation is doing and how that could affect the direction that your forces are pointing in. Okay, let's look at one more example before we get into things rolling down inclines. Okay, let's say this time we have a yo-yo. And if you know anything about a yo-yo, you know that it is basically like a spool with thread in the middle, and we're going to treat it like a disc. We're going to treat it just like a flat disc. So let's say that this is like us looking at the yo-yo from the side, and then in the middle of the yo-yo, if we were to like look on the other side, there would be this little internal disc where the string is. Okay, and let's say that the string of the yo-yo is wrapped around this, and let's say that the string is coming out right here, and we apply a force of tension right there. So this is different from that last cylinder problem we did in two ways. The first way is that I have like 2 points of contact that have different radii, different distances from the axis of rotation. The axis of rotation is right here, okay? Let's say that the outer radius of this whole thing, let's just say that it is r. And let's say that this inner radius right here is r over 2. Okay? So this is complicated because we know right away, just like last time, we're thinking about two things: translational motion, rotational motion. And for the rotational motion, I have two torques that I'm going to be worried about. I have this force of tension that's providing a torque right here. And then I have the torque, of course, from the static frictional force down there. So just like last time, before we can slap a static friction force on here, we're going to have to pause and think about what direction is it acting in. Remember last time we had it acting to the right, helping the force of tension? We don't necessarily know if that's going to be the case this time. Okay? So here's what I need to think about. I need to think about, first of all, under these circumstances, what is the thing going to be doing translationally? What's it going to be doing rotationally? What has to be true about the forces for that to occur? Well, by supplying this force of tension, this is a large force of tension to the right, I can make a pretty good assumption that the translational acceleration will be to the right as well. Okay? So because the thing is translationally, linearly accelerating to the right, that is going to help me think about what it is doing rotationally. Once again, key idea here, if all this is happening without slipping or skidding, in other words, this point does not slip or skid over the surface as it rolls, I know that any translational quantity is going to be related to the rotational quantity just like this. This is always true only for objects rolling across surfaces without slipping. All right. In other words, the acceleration translationally of the center of mass or of the whole body itself is going to be related to the angular acceleration. So if the acceleration is to the right, going this way, I know, therefore, that the rotational acceleration must correspond to that. They have to have the same sign. They have to be going together. In other words, if the translational acceleration is to the right, then the rotational acceleration has got to be clockwise just like that. I know that a point right here must have an acceleration that way. And so the rotational acceleration must be clockwise. All right? So that has got to be the case. But now you can see that this leads me to interesting conclusions about my two forces, my force of tension and my static force. Is the force of tension responsible for supplying the torque that is causing that angular acceleration? The answer is no. It's in the wrong direction, isn't it? That force of tension should be causing the thing, if that was the only torque, it should be causing it to rotate counterclockwise, because that is the direction of the torque of the force of tension right here at this point of application. Does that make sense? If you need to think through that in terms of the direction of torque, if I draw this vector here from the axis of rotation to the point of application, and the fingers of my right hand follow that. I curl my fingers of my right hand to the right. My thumb is pointing towards me. It's pointing out of the screen. That is supplying a torque. The torque due to tension is coming out of the screen at me. That's positive. That, you guys know, is associated with counterclockwise acceleration, a rotational acceleration. So this tension force then is actually going against the rotational acceleration I know I have. Once again, how do I know that the rotational acceleration actually has got to be clockwise? It's because when things roll without slipping, this statement right here is true. So whatever the center of mass is doing, aka whatever the whole system is doing translationally, must correspond to what the rotational acceleration is doing. And because the whole system is translating in acceleration to the right, I know that the rotation has to correspond to that, counterclockwise. I've just shown you that the torque supplied by this tension force is going counterclockwise. So that tension force cannot be causing that torque. So what is? It's got to be the force of static friction here, huh? And the force of static friction to cause rotation, to cause the actual rotation that I have clockwise, has got to be pointing back to the left, doesn't it? So this is the opposite of what we saw last time. Now my force of static friction is pointing back that way. Okay, so let's try to analyze Newton's laws here. Normal force, force of gravity, force of tension, force of static friction. Sum of the forces, force of tension minus force of static friction, equals the mass of the thing times A. So there's, what we've always been doing. And then rotationally, I need to actually draw it out. Here's one force. Here's another force. That's my force of tension, force of static friction. I'm worried about torques this time. So you guys can see and get the feel for this problem-solving process. We're always going to do Newton's laws now in two different ways. Translationally, where we collapse it down to a point particle to think about what's happening to the center of mass. And then our extended free body diagram, where we think about where the forces are located to the axis of rotation so that we can think about the torques. Now let me remind you that earlier we said that this whole thing has a radius of big R, and this tension force where the string is spooled around the interior of the yo-yo is at a radius of big R over 2. So when I go to write my Newton's second law for that, sum of the torques is I alpha. Remember that we always want to set as positive the one that is agreeing with the acceleration. We know that this thing is accelerating around clockwise. Which torque is agreeing with that? That's this one. So that one's going to be my accelerative positive torque. Remember that torque is R cross F, and the distance that this force is away from the axis of rotation is, of course, the entire radius R, and the angle between them would be a 90-degree angle, so RF sine theta would just collapse into RF. So R times the force of static friction minus the torque due to the tension force, which is going to be R over 2 times the force of tension, equals I, and of course the I for a disk is 1/2 mr squared times alpha. And then again, we know that alpha R is equal to A, therefore alpha equals A over R. We could sub that in here, and then we could begin to solve for our variables. So I just want you guys to get the hang of our new problem solving strategy here. We're analyzing it at like a point particle to figure out what's happening overall to the acceleration of the body, of the center of mass, as we say. And then we're doing another free body diagram of the extended object, thinking about where the forces are, and our directionality is different now, right? This is contributing a negative torque, because if you use the right hand rule, it's pointing the opposite way. Or if you just think that this force is supplying a torque that is accelerating the thing, and this one is supplying a torque that is opposing that. So we have to count it as negative. And remember, the definition of torque is R cross F, where R is the position vector from the axis of rotation to the point of application of the force. That's where the R over 2 comes from for the torque due to the tension force there. So it's interesting that just by having the string, in this case, kind of on the underside, our frictional force now all of a sudden has swapped direction compared to our last example. So you've got to be much more flexible with these types of problems. Whenever we are considering something rotating, you've got to be used to being flexible and pausing and thinking very carefully about, first of all, the direction of acceleration, and then what that means about, as long as it's not slipping, what that means about the direction of angular acceleration, and what that means for the directionality and the strengths of your forces and your torques. Okay? All right. In fact, why don't we go ahead and see here what happens when we plug in A over R for alpha. We get R, force of static friction, minus R over 2, force of tension, is going to equal 1/2 m. I'm going to get R squared over R, which just leaves an RA. You can see algebraically that all these R's will cancel out. So force of static friction minus 1/2 force of tension equals 1/2 MA. And now we could combine these two equations, our translational equation, our rotational equation, and we could start to solve for some things. We could even, compare the strengths of these two forces if we wanted to. I'll leave that algebra up to you. Rolling without slipping, we know that the velocity of the center of mass is equal to the tangential velocity along the wheel or along the object that's rolling. And we know that's equal to r omega. If there's acceleration, we know the acceleration of the center of mass is equal to the acceleration of a point on the edge of the rolling object, which equals r alpha. We know that we use a force of friction static, force of static friction is used because this point right here has an instantaneous velocity that's equal to 0. It's instantaneously motionless. So there's a static frictional interaction, and that is what provides the torque if there is indeed an alpha. All right. One more thing that I did not mention. These things you absolutely need to memorize. Here's another thing that I did not mention, and that is that in this case, kinetic energy is perfectly conserved. In other words, I'm going to say this: friction does no work to dissipate energy away. Remember that work is defined as a force, so F dot dx. That's the general term if these things are constant. It's just the net force times delta x. Well, my frictional force is really not acting over any distance. It's only acting at a certain point, right? So friction is not doing work to sap any energy away. So my kinetic energy is perfectly conserved. That will be important a little bit later. So all this is true for rolling without slipping. I think that it goes without saying that the exact opposite of all of this is true for an object that's rolling and slipping over the surface that it's rolling on. So what we need to do now is work out an example problem, super important example problem, where we have an object that's rolling down an incline and it's rolling without slipping. So let's look at that.